So my name is Juno Choi and I am from Yonsei University in Korea. So I would like to present our paper titled KAIROS, Talking Heads and Moving Bodies for Successful Meetings. So this work was done during the summer internship program last year in Social Dynamics team, Nokia Bell Labs Cambridge in UK. So let me start my presentation. So meetings are the fuel of productivity, and meetings are essential to have an organizational life. And it is known that up to 55 million meetings are proceeded every day in the United States. But recently, we all know that the world transitions from the offline physical meetings to online virtual meetings. And Microsoft recently reported that there are almost 3 billion minutes of meetings are proceeded each day. And this is basically a phenomenon that has been going on now and just before the current pandemic situation. So considering that, there is a slightly different picture of meetings engagement in virtual meetings. In offline meetings, both visual and nonverbal communication cues exist, where nonverbal cues include body postures and gestures. In virtual meetings, however, only audio-visual communication cues exist, and it is hard to interpret nonverbal cues expressed by meeting participants, like body postures and gestures. So assume that we have an online presentation, like what we are doing right now. In the speaker's perspective, it is very hard to capture participants' moods because only audio-visual information is available. And it is so hard to see all participants during showing presentation slides. So at this point, I am also very hard to interpret the current mood of your participants. And what about the other types of online meetings? In this situation, participants can see the other people simultaneously. However, some participants may feel uncomfortable to share their video streams, which may even harder to capture visual cues in virtual meetings than offline meetings. So in this session, we also have many people are closing their cameras, so it may even harder to capture those kind of cues. So this leaves virtual meetings have missed opportunity to read the room. So previously, many researchers have been investigating on meetings, but usually for offline meetings. And as I mentioned earlier, the picture in virtual meetings may slightly differ than that in offline meetings. And the studies are focused only on single modality, like audio-visual information. This means that the full spectrum of humans' nonverbal body cues has not been captured effectively. So to tackle this, we employed a multi-sensory approach that can capture body cues, which includes the smartphone and its peripheral devices. In this study, we deployed it in 55 real-world corporate virtual meetings. We also developed 6 body cues metrics based on the literature and tested whether they are predictive of meeting success by building a prediction model, which predicts success from our 6 body cues metrics. Finally, we performed a thematic analysis, which provides 3 types of key phases in a meeting that happen to greatly impact its success. So, in this talk, I will first introduce our system named KAIROS for multimodal monitoring of virtual meetings. Then I will explain the experimental setup for our user study and 6 body cues. Next, I will show the results of our prediction model for predicting meeting success from body cue metrics. And finally, I will explain 3 types of key phases in a meeting that we found. So let me first introduce our KAIROS system, a system for multimodal monitoring of virtual meetings. So our system mainly consists of 4 parts: a mobile application, a smartwatch application, earbuds, and a web server. So as shown in this illustration, each participant uses our mobile application along with wearable devices, and our web server aggregates data obtained from multiple participants. So the first component is the mobile application. It is implemented with a hybrid approach, which means that the user interface is implemented using HTML5 and JavaScript, while native functionalities are implemented using Swift on iOS and Kotlin on Android. This enabled us to keep the user-facing elements consistent on both iOS and Android platforms, and optimized the sensor data collection for each platform independently. The mobile application collects motion data from the device's own sensors. Also, the mobile application operates as a local server, which handles collected data from Bluetooth-based wearable devices and transmits the aggregate sensor data to our web server. The second one is the Smartwatch application. It is implemented with Tizen OS that runs on Samsung Galaxy Watch devices. Our smartwatch application collects motion data from the watch accelerometer and gyroscope sensors. And additionally, it collects heart rate from the device's PPG sensor. And it transmits data to our mobile application by using the Bluetooth low energy technology. And the third one is the earbuds. We considered an experimental device called eSense, which is a new kind of earbud devices with advanced sensing capabilities such as IMU sensors. And thanks to the eSense platform, we collected motion data from its accelerometer and gyroscope sensors. And similarly to smartwatch, the collected data is transmitted to our mobile application by using the BLE technology. And the last one is the web server. We implemented a RESTful web server using the Python Tornado framework that communicates with our mobile application. And all the sensor data is stored in our MongoDB-based database instance efficiently. Also, our web server contains an audio broker service, which records the audio of an online meeting. Now let's move on to our experimental setup, which includes user study, dataset, and analysis. We conducted the experiment for 3 weeks. First, we deployed our mobile application using a test flight deployment for iOS devices and a direct Android package deployment for Android devices. And before we started our user study, we had an online 60-minute onboarding session to instruct our participants. A total of 55 real-world meetings data having about 2,000 minutes in length are collected. And we also collected post-meeting questionnaires having 2 questions, which represent our process for meeting success. And these questions were from our previous large-scale crowdsourcing study, which was conducted to understand what affects people's perceived experience during meetings. And that study was presented on the last UDCOM conference. From 3 devices like phone, watch, and earbuds, we collected data from these sensors. Also, we collected audio data from our audio broker service and extracted some common audio features. And the audio features are used along with the other sensor data in constructing our body cues metrics. Upon the raw sensor data obtained from various devices, we designed 6 literature-driven body cues metrics that reflect a meeting success. And these are vibrancy, multitasking, heart rate, head movement, postures, and hand movement. First, previous studies found that vibrancy in speech is highly related to engagement. From that point, we calculated the body vibrancy metric from the audio features, and a larger value means more conversational and vibrant meeting. Second, we consider the multitasking metric, which can capture the phone usages during the meeting. This metric is calculated from the phone's motion sensor readings, and a larger value means the more the smartphone has been moved about. And third, we consider the heart rate metric, which is calculated directly from the negative value of the heart rate readings. Therefore, a larger value means the lower heart rate during meeting, which indicates more focus on the meeting, because it is known that lower heart rate were associated with focus and consciousness. Fourth, we consider the head movement metric that can capture head gestures. It is calculated from earbuds gyroscope sensor readings, and a larger value means the participants move the head more frequently. And fifth, to capture people's attitudes during meetings, we consider the posture metrics that is calculated from ear-over accelerometer sensor readings. And a larger value means the participant changed posture with the larger movement. And finally, we consider the hand movement metric that captures hand motions and gestures. And it is calculated from the smartwatch's motion sensor readings. And a larger value means the more hands and wrist movements. Along with the 6 body cues metrics, we also set our target ground truth values from the post-meeting answers. And as I mentioned earlier, these questions are from our previous large-scale crowdsourcing study here. And based on the loading factors from the PCA analysis in the previous study, we obtained the aggregated scores from this equation. In addition, because the survey scores are skewed, instead of using aggregate scores directly, we binarize them using median values computed across all meetings gamma scores for each participant. Now we have both 6 body metrics as inputs and target ground truth to predict meeting success. So let's move on to the prediction of meeting success from the body metrics. In this study, we consider a random forest model because we found that it showed better performance than other models like SVM and logistic regression. And our model achieved 79% area under curve or AUC. And when we investigate the feature importance of the random forest model, we found that the head was the most predictive one. This suggests that head gestures were highly related to success. And hands was the next most predictive one, which was followed by postures. Surprisingly, vibrancy was the least predictive one. And we speculate that because the meeting format was corporate meetings, so not everyone might get the chance to speak up and contribute. And we further investigate the predictive power of 6 body cues metrics by deploying 2 additional random forest models. The first one was built upon a sentimental feature. To obtain the sentimental feature, we first transcribed audio recordings using Google Speech-to-Text API and performed a bag-of-word-based sentimental analysis to calculate the fraction of positive over positive and negative words in the meeting's transcript. This prediction model may rely on emotional content rather than body cues to predict meeting success. And the second one was built only on the head metric, which showed the most predictive power. And the AUC scores show that the head movements are more predictive than content, and body cues are much more predictive than content information. While our prediction works well, we further zoom into meetings to understand its temporal dynamics. So let me show you our findings during meetings. To do this, we conducted a thematic analysis on the meetings by windowing them with 5-minute windows. Because each meeting can have its own variety, we consider calculating z-scores from our random forest model. So it enables us to investigate the dynamics of each meeting separately. From 10 randomly chosen meetings, we identified 3 typical phases that impacted meeting success, which are initiation, collective discussion, and turning points. In this figure, blue points refer to z-scores greater than 0, which present positive contribution to a meeting success, and red points refers to negative z-scores, which presents negative contribution to success. So, first is initiation, which is a period in which participants set up their devices like cameras and microphones and wait for other participants. These periods are measured as negative, suggesting that a large initiation period negatively contributes to meeting success. We also found that vibrancy and heart rate were underexpressed. And the second is collective discussions. We observed that the central parts of most meetings typically unfolded into 2 phases, which are presentation or discussion. During the presentation phase, only one person is talking. However, in a discussion phase, it consists of multiple people having a conversation. So during the phase, both agreements like okay, sounds good, and disagreements like that's right, but I mean, are frequently occurred. And we found that discussion periods are associated with positive contribution to success. And we also found that vibrancy, hand movements, and postural metrics were overexpressed. And the last one is turning points. These phases are observed when the topic changes, a latecomer joins, a question is raised, and so on. So these phases contribute positively to meeting success. So by listening to the audio, we found that these periods stimulates attendees to refocus on the meeting. So now let me conclude our work. Virtual meetings have limited sensing capabilities for both visual and nonverbal cues. So to reduce the gap between different pictures of the virtual and offline meetings, we presented our system named KAIROS that collects data from mobile, smartwatches, and wearable devices and translate it into 6 body cues metrics. So this gives us an opportunity to read the virtual room. So what can be the next? With this opportunity, our system can improve virtual meeting experience with feedbacks like visualization of aggregated body cues, manipulating audio features, or delivering haptic feedbacks on smartphones or smartwatches. Our system can also be expanded to various types of meetings, such as town hall meetings, all-hands meetings, online lectures, and so on. And finally, we only used wearable devices and smartphones' motion sensors, but our studies can enrich the sensed modalities through camera-based head motion and facial gesture detection and so on. So thank you for your listening.